All right, let's start. Welcome everyone. This is first lecture on planning algorithms course. Today I'm just gonna give like a brief introduction to what we mean by planning, right? So this has meaning in different fields. So we'll see that in robotics, they understand one thing, in AI, controls, etc., etc. And with this kind of introductory material, we will start developing courses, lectures over the course, right? So, yes. First thing that I want to answer is, who are we, right? So I'm Professor Ferrer. You can call me Gonzalo. This is my email. You can also reach me by Telegram. Maybe this is going to be the preferred way of communication. We have our awesome team here also present today. So we have Alexander Gamayunov and Timur Akhtiamov. They will be helping us developing some materials, giving some seminars with problem sets, right? So we are together team of this course. A little bit about us, apart from the course, right? So we are part of the Mobile Robotics Lab. So some of the topics that we do research on is path planning, robot navigation. We also do human motion prediction. And these are kind of topics that are well aligned with content of this course. We also have other research topics that are more related to perception, in this case, sensor fusion, visual SLAM, localization, state estimation, others that are still, I think, interesting for robotics, but we will not treat them too much in this course. You can also check out our webpage here. And I think, yes, this is kind of brief introduction. I don't want to do like this course exclusively in robotics, and you will see why when I give this definition of what planning is, right? But our background comes from robotics. So this is, we are a little biased into this, but I don't think it's a big issue, because for the understanding of all the methods we'll be presenting, we'll try not to give only robotic examples, but a little more general ones. So what is planning, right? As I said, planning has different meanings, or at least it's a topic that is used like broadly in different disciplines. And let's start with robotics, right? There's terms that change from one field to the other, and I will try to put all of them together, right? For you to get like this big idea of what planning is. So in the context of robotics, this involves these high-level specifications of a task into small actions that then later we take on. And the most clear example of this is the piano problem, right? The piano problem is very simple. We have this piano here in red. We have a lot of obstacles. We have, in this case, a region. And the problem is how to move the piano such that you can get from one room to the other. Now you see that this piano has like an orientation, right? We'll talk about this. So this is part of its state variables. But the idea is basically this: how to get this high-level specification would be from the initial point outside the room, how to make, how to create a trajectory or a path that allows us to bring this piano inside the room, of course, without breaking our house, right? So you see that sometimes you need to rotate, you need to move it. Well, the problem is complex. So far, it has been subject of study for research, so it's not just like a toy problem, but a little more involved. But this is the idea, basically, from point A to point B, right? This problem planning, let's say in general planning, it's also known as motion planning or path planning. Path planning includes just a sequence of state variables or poses for the piano, because, well, this is orientation and position. But in general, it's just a sequence of these poses. if we want to take into account time, then this is also called trajectories, right? But this would be probably a little more advanced topics not to be covered in this course. So this is for when we consider kinematics and other stuff. Okay. No, this one is already shown. So other examples might not be including 3D, right? So 3D, I think it's hard example to start with, but there's a very good examples in 2D, right? And in 2D, we can have like this one, right? So for instance, we have a stick that we are moving around some objects. Still, it doesn't mean that the state space is 2D, because you see we have position and orientation. And we will spend just a class talking about this. But what a plan means is that we are going to move this object around from this starting configuration to a goal configuration, and we want to avoid obstacles. In this case, these kind of circles. Can I play this again? Okay, so in the first view, we don't care about optimality. We just care if there's a plan. If one exists, then, and that's what we consider feasibility, right? If it's possible to do this plan, in this case, bringing this rod from this point to the other, right? Later, we will consider other little details, such as optimality. So can you do this, like, I don't know, in minimum time, or being farther away from obstacles as possible. And we will also talk about uncertainty, because well, the world is uncertain, and for some examples, this is a serious issue, right? So uncertainty involves all this stochasticity in the world, and well, we'll cover this in lecture, I think from lecture 7. So for now, don't have like too much worries about this. Another example of the piano problem is solving like this 3D maze in robotics. So imagine you have like this screen L and you want to move around this maze. And the problem is very similar, right? So now instead of having walls, you have other objects, but still the idea is that you want to avoid collisions, right? In this case, well, collisions, let's say, that are part of this feasible plan. So no collisions is feasible plan. If you have collisions, that means that the plan is unfeasible. We will not cover dynamics, as I said at the beginning, right? So we will just start with paths. So paths, imagine them as the sequence of this, for instance, this L-shaped thing that moves around over the maze, right? But as I said, if we have here sequences of states over time with timestamps, then this is what we call a trajectory. Okay, so I think that's enough from robotics. It's clear what moving a piano means. We'll be working on this. We'll see that there's different techniques to solve this problem, right? So in general, this is what planning means in this course. From control theory, this is something that people have been also studying, right? The thing is, control usually considers physical systems, and that means that there are some differential constraints because, well, you need to have a smoothness over these systems and etc. Right? So for instance, in these examples, what we see is that these are all inverted pendulums or acrobot or carpal, very popular examples I'm sure that you've seen. And in control, people don't talk about plans, right? They talk about controllers, right? Or control laws. So this is a little change of nomenclature, but at the end, it's the same idea, right? So for instance, in case of pendulum, you want the pendulum to be, I don't know, vertical position, like in this unstable equilibrium position, or in the case of the carpal, you want just to stay up without moving too much, right? So in this case, that will be the plan, but for controls, we'll call this like control laws, right? Like what are the actions that are allowing us to fulfill these objectives, right? Usually controls also focus more on optimality, stability, and other things. But if you think this as a sequence of states, it has a lot of overlapping with path planning. So it's interesting. Maybe some of you have backgrounds on automation and control theory, I'm sure. So many of the things we will be discussing here could be well, you will sound familiar. Let's move on, right? So artificial intelligence. So for artificial intelligence, it's again kind of same. The problem is also interesting to be solved, but in this case, what we have instead of a plan, what we have is agent or decision makers, right? And then usually they refer as, instead of planning, problem solving, right? So we have a problem and we want to solve it. Could be move the piano, could be in this case, like very famous one, just solve this Kubik's cube. Usually it's not so centered in systems, right? Like a system that evolves over time or has like positions and orientation and these things in a 3D world where we live. But usually it's more abstract things. So for instance, here we'll see like how you take the cube, right? So then you need to decide what is your state space. Usually, well, the way of solving is the same, but let's say that the considerations are a little bit different, right? So in this case, I don't know, states could be like each configuration of the cube. You want to take actions. That means moving the blocks inside the cube. In this case, well, this person is very fast doing this, but actually, if you think about it, he kind of solves the plan ahead. So now he's solving the plan, and now he's just executing, like moving things faster. Still, this could be a definition of planning as well, right? So we have initial state A, cube unsolved with not uniform colors, and our target state is have all of them of the same color. Okay, so let's discuss about this general idea that includes all these disciplines talking about the same concept, right? So this is what I'm calling this planning to plan. It means different things, right, in different disciplines. So I just give like some examples in robotics, artificial intelligence, control theory, and so on, right? So in this course, we'll try to give a unified view. Again, there's a lot of specifics on each of the fields, right? But because this is kind of introductory material, we will not get into dynamics, right? So I think all these things are common for all these disciplines. So in this case, in this circle, it's all elements that we consider kind of agents, robot, controller, player, decision maker, right? All of these are synonyms, so they are referring to the same thing. Usually in this course, we will refer to agents or robots, whatever you prefer. Then are all these elements, right? And what we have is a planner, right? So planner is kind of our algorithm or problem solving. It's our algorithm that is going to give us like this solution. And what is the solution? Well, it's here in this other red circle, right? Sometimes the solution could be called a plan. Others could be called a path, like this sequence of positions. Trajectory, this is what I discussed. If you add time here, and then you need to fulfill also not state variables, but time. Policy could be also your solution. So at for every state variable, you have a policy to execute that is giving you an action or a distribution of actions, that depends. We'll cover this later. We'll start with trajectories and paths, by the way, or control laws, right? So this will be, if you want your solution, this will be the algorithm kind of calculating this solution. And you can consider this, kind of your state variables or a little bit of what is the thing that needs to plan, right? This is very abstract, by the way, very abstract way of thinking about it. But in general, I think this unified view will help you depending on which background you have and what you want to do. This is the same view as Laval's book. So this is recommended book. You can check out in Canvas. We have a digital copy, and I think the author also shared with the world free available copy on his webpage, so you can check out. It's really, really good book. We'll follow parts of it, right? So when there's like content included in the book, I will say in the slides. So then later, if you want to go deeper, you can check out. But okay, let's say that this is just to talk about this unified view on what planning is. Okay. So if there's comments or questions, maybe now it's time to ask. If not, well, let's say that this is a very general thing. I'm sure that most of you are familiar with this, so maybe it makes sense because you were working on a similar problem. At the end, the nomenclature is not so important. What matters is identifying like parts, right? So the algorithm, the solution, and the states. So let me put a little more formally, well, not very formal, but a little more formally, which are these ingredients for planning, right? I have talked so far about state, right? So states are all possible situations that could arise. In case of the piano, are how the piano is oriented and how the piano is positioned in the 3D world. In case of the stick, is the same, but on the plane, so the plane. Actions, they change states, right? So you can think about it, and every time that you apply an action, well, potentially you can change the state. This has also many names, so usually it could be called as inputs, controls, operations, etc., etc. We'll refer them as actions, right? So, but just know that these are interchangeable terms. Initial and goal states, right? So we have discussed that this is one of the key ingredients because you need something you start with, piano being outside your house, or the cube, Rubik cube unordered, right? This will be your initial state. And then you need a goal state, right? Like, how do you want this to be at the end? Like, for instance, the piano inside, you entering a door, or solving the Rubik's cube. Sorry. Okay, we also need a criterion, right? And this might sound a little trivial, but it has subtle differences, right? So this is the desired outcome of the plan. And we have discussed like two of them so far, right? The first one is feasibility. You just want to get, you don't care how you do it. Sometimes the problems that could be considered are so difficult that you don't really care about other things. You just care if there's a solution, I just want to find it. Okay, why is this? Because maybe you have high dimensional state variables, maybe you have many, your action space is also huge. There might be reasons for this, right? The second one that is a little more strict criterion is optimality. So the criterion for optimality is, first of all, you need a feasible plan, right? So if you don't solve the plan, you cannot say that this is a good criterion, right? So you need to solve it in terms of the goal state. And then what you need is to define a new function that is gonna provide like some value, and this is the objective you want to optimize, right? So this is a little open question. What is this objective? How are you creating cost functions? For now, let's say that there is one, and well, you want to find a path or a solution that solves your problem and also has minimum optimality conditions. And of course, we have a solution, right? What we have called a plan. So this is just specific strategy or behavior, could be a sequence. So you know exactly what you need to do at every position. It could be a policy. So a policy is actually a very powerful way of solving because it tells you what to do at every possible state space, which is kind of amazing thing, right? So it's not just a particular sequence, but it's going to be telling you what to do all the time. You just apply your policy. Right, so we'll see that there's very efficient ways of calculating policies. Actually, this is also most of the things that current learning-based approaches are kind of approximating policies, right? We'll get into this, so don't worry, we will explain this from the beginning, in a way that is very understandable, and you will see like very quickly how powerful these approaches can be. Okay, yes. Let me give some examples. Maybe I already gave, but let's try to identify all these components that I was talking about the piano movers problem, right? So what is the state? State are 3D poses. Maybe some of you are familiar with what is a 3D pose, but let me just explain. It's an orientation in 3D. It's usually represented with a rotation matrix or 3 angles, but this is a little tricky. Don't worry, we will not get into well, SE3 and all these group of rotations and translations, but it could be a position and orientation in the world, right? So why it matters? Because the piano is not symmetric. It's not a sphere, right? So there's dimensions that, for instance, are longer in the X direction, but not on the Y, right? So it's asymmetric. What are the actions? So the action is you move the piano, right? So imagine you slightly move it around, and this could be relative poses, right? So imagine a relative pose is just a little change with respect to your previous pose. So imagine here you're just moving, getting closer to the camera, or maybe you are rotating, and in this case, you're rotating with respect to the Z axis. Let's call them relative poses, okay? Still, you could have like a discrete set of actions, by the way, which are all of them relative poses, or you could have an infinite set of continuous actions. That's a little bit depends on how you want to formulate the problem. Let's talk about the initial state. You are in the corridor, you are outside. You want to put this inside your house, right? So this will be your goal. Put this in your house, in your office, somewhere, okay? What is the planner, right? So what is the algorithm that you are going to be using to handle this situation? And this problem is complicated because you have 6 degrees of freedom. You have multiple collision checkings that you need to do right over time because there's walls, there's other objects, right? So an algorithm that we could be using is something that we will explain in lecture 4 that is called RRT, okay, rapidly random exploring trees. And then the plan is, as I said, just a sequence of actions. This, by the way, is an example of that you will get. There's a priori on this algorithm no optimality, so you will just get a solution. Maybe you go around the building and then you finally enter your house. Still, you succeed, but let's say that it's not optimal in terms of time. For some problems, this is hard enough. I cannot stress on this enough. So sometimes it's just a question if there's a solution or not. Maybe you don't see a solution. Maybe the piano is too big and there's no way that you are going to enter that through your door, right? So this is a solution you want to find out. You don't care how. You just want to find a solution if there's one, right? Okay, second example could be like, for instance, this is a little more abstract, how to arrange your furniture in your house, right? So at the beginning, this state could be positions of all objects. The actions could be moving objects. And then let's say that your initial state is empty space, you just move on. And the goal is have this IKEA picture that you see on magazines, right? That never happens. So, I guess, yeah, we are like bad planners in terms of feasibility. We never realize this picture. But why? Because the planner is ourselves. So we are kind of the algorithm, the guys doing this. And this is a little known principle, right? So this is not an algorithm we will be discussing, but you could consider yourself as planners for achieving tasks. And then at the end, well, this will be just a sequence of actions. Okay, I'm sure that all of you can come up with an example, think about it, of a simple task that you can define in these terms, right? Defining a state variable, action space, or action variables, initial, goal, etc., etc. Okay. Now let's get into this taxonomy of planning because I have just explained big picture. But there's different variants, right, that could be including a plan, right? So this one that I have just described, the piano mover problem, you can consider this as an open loop execution. So what it means, you have your plan, you have your solution. You know that you need to follow this sequence of movements, maybe rotating the piano, then moving, going back, then down, whatever it is, right? And this is what we call an open loop execution, right? So you just execute this plan and you know that it will provide you a feasible solution. You will get to this goal state that you are looking for. Now, what happens? Sometimes, for several reasons, maybe this is not good enough for you. Maybe what you want is, while you're executing, allowing to have a little bit of disturbances, right? And this is the idea of now providing a plan that allows you to correct for these little errors, right? So in this case, there's going to be an environment. Maybe the environment is adding noise to whatever you think you're executing. So that's why you need this feedback plan. So I have presented a little bit, but this is the idea of a policy. Sometimes you have local policies only close to your path. Imagine you have calculated a solution and you can perturb a little bit. And outside this small region, you don't know. You don't have guarantees because you don't have calculated anything, right? So there's still like this idea of having robustness to small changes that I think is very interesting for some problems. Let's talk about this other one, which is refinement. So what it means, you kind of calculate a core solution, right? This core solution might be, okay, how is it possible that I can get from, I don't know, new campus to Moscow Center, right? So then you do a plan, okay, take the metro, then bus, then you walk. Okay, fine, this is good. And then you want to do refinement. So refinement, maybe it's just telling you like lower level actions, like move your left feet, move your right feet. Okay, maybe this is an exaggeration, but you get the idea, right? So there's usually this is described as a hierarchy of states, and sometimes you want to start with this high level description. Why? Because it's going to be faster, and then you can do refinement over this solution, right? And the number of layers, it could be like as many as you want, right? It depends on the level of detail you are looking for. For instance, we see this with cars, right? So you're moving on the highway, you know that your plan is just going, I don't know, straight to Moscow, right? So you are looking at all this. And then there's a refinement plan that is telling you, okay, now you should be moving to the right lane, you should be going at this speed, right? So now the action is a little bit different. Instead of just going straight, it's like lower level actions that you take for your car. And well, let's say that hierarchical plan is kind of subset of this refinement structure, right? So we could have like hierarchies. In this case, each of them is included into the other, right? So these two are very similar, right? So sometimes it's question, right? If you want to improve or you just have a hierarchy. Well, anyway, this usually responds to the motivation of you break down the problem, you make it simpler, and then you go deeper and solve like fine level details with smaller state space for you to solve, right? Okay, we'll see examples of all of them, don't worry. But I think mostly this covers all the taxonomy of plannings we'll have. We will start talking about this, open loop executions, then feedback, and then we'll see that this comes very natural, right? So these are just, each of these are kind of building blocks that are gonna be part of this refinement or hierarchical approach. Okay, so let's talk about the course goals. Main goal is that you become confident on solving planning problems. So what it means is that you need to identify like what is the right tool for using. In this case, we will cover like a different set of problems, including discrete planning, continuous planning, decision making, planning under uncertainty, and learn-based approaches, right? So these are like very wide, different problems, right? And of course, each of them could have like many algorithms, but we will just give the basics. From here, I think you can develop like your own tools if you need to study more or do research on this topic or work on a problem that requires like this kind of algorithms, right? So it's very important to choose the right tool. It's true for every problem, not just in planning, but choosing the right tool is key, right? So that's why we are giving like this overview of these different kind of problems, and then you need to identify if your problem could be classified as these kind of these categories that we have studied. Prerequisites, not really. Basic programming Python skills, so we'll be providing our problem sets in Python. So it doesn't mean that you need to be expert, right? But if you are not familiar with Python, at least you need to put more time to catch up and learn about Python. It's not just useful for this class. It's going to be recurrent. I think it's the default language for programming used in many courses at Skoltech. So if you are not familiar with Python, I think it's a good introductory. Well, at some point you need to start doing this, right? But I would say that yes, it's a prerequisite. Either you know it or you are willing to learn Python. Okay. A little bit of probability, not really much, so it's going to be self-contained, right? But I want you to be familiar with what probability is. We will not go like so into detail, but knowing about PDFs, what a conditioning random variable is, all these things, right? Like things that I'm sure you have done in your undergrads. And next steps, following a little bit on the robotics trend, we'll do a course, Perception in Robotics, in term 3, that includes all these perception problems that I was talking about. The two things complement very well. So I think this is kind of a research topic. Planning sometimes assumes perfect observations or noise that is very particular. Perception also assumes that your plan is going to be executed as you want, but there's not much interaction between the two. So I think knowing about these two topics could be interesting if you want to go deeper into robotics, right? But again, this course was not about robotics. It's more planning in general in AI and many other fields. Okay, so what are the learning outcomes? As I said, you will have theoretical knowledge, right? So we'll develop the algorithms and you will have practical skills after doing problem sets. So this is the only way. You sitting and coding. Imagine that later you want to design your own things for decision making, for AI. No matter what, you will have to start with these two skills, right? So you need to understand the principles, why these algorithms work, and then you need some practical skills on implementing. And I'm sure that problems can be more elaborated, more complicated, but in the course we'll give you tools to start understanding, like get this grasp of what planning is and how to solve it. You will also be able to analyze problems, right? So that means you need to identify what are the ingredients, what is your state in your problem, how can you use this, is there like other representation you can use, what is your action space, do you need a continuous set, do you need a discrete set? These are questions that you can answer, I think, after having some experience or some hands-on on some problems. So this is what the course is giving you. And then, well, as I said, yes, you get this experience, right? So, of course, yes, we want this to be enjoyable experience. So I think we can learn and also have fun. So you will see that some of the problem sets are really fun once you solve them, right? Because you are kind of animating your agents or your mechanism or your robot, right, into doing whatever you want, even if it's just going from point A to point B. So you will see, maybe some of you find this enjoyable. I at least find it interesting. And well, anyway, you can say at the end of the course if you like it or not. Okay, Very good. Now, I think this was like all from kind of motivation or context around planning, and I'm gonna go on specifics for the course, right? So maybe before I move on, we can do a little break. So it could be good if, I mean, it's not break that you go. Let's do a break like the following way, right? So maybe if someone has questions or some comments or something, maybe we can comment before we move on. So it's not really, well, part of the presentation, but maybe it's a good point just to get back to some of the things. Who had heard before term planning or control law or decision making before? Can you write on chat a plus like this? Okay, we see a lot of pluses. Okay. So maybe, yeah, I also see my TA. Yes. The thing is, it's okay to have some background. I think probably will give like diverse, very wide view, right? So maybe some of you have already are familiar with discrete planning methods, right? So this is the most common one. Maybe I think some courses were covering part of them, but maybe there's other parts that you are not so familiar, right? So we will cover all of them together in a comprehensive way. Okay, it's very good. It's very good. What else? Is someone here from background on controls or control theory? Or did you do classes? Yes. Okay, we have one. Plus, plus. Okay, we have plus. Okay. Okay, yes. I think that it's not total overlap. So I think it's a little orthogonal because the way we are presenting things, as I said, is not stressing so much into dynamic systems, right, and optimality. You will see that we start more with kind of exhaustive approach, right? So discretization, and from here we are going to build the story. But I think this can be like good starting point for you. If you don't have experience on this, don't worry, because as I said, the content is self-explanatory. So yes. Okay. So if we don't have more comments or no one has like other comments on this, I think it was like very illustrative, right? So we didn't get into any algorithm or any equation so far. So it was like high level, more story if you want. So if that part is clear, let's get into the structural details about the class, right? So I'm sure everyone is also interested in knowing about this. Monday, Friday. So course will be online. I cannot say. These two first core lectures will be online. After a third one, I will do an announcement, but it depends a little bit on policy that Skoltech is gonna follow, right? So I think yes. So in principle, from the educational department, people were saying that this term will be offline, is called, like in person, but I cannot guarantee. So we'll just do announcements once we have like official response. Okay, yes, that's great. Okay. So we have these 2 days. That's what I'm not writing. We have a class assigned, but at the moment we do offline, I will put it. I think it's 3006. It's in Canvas. Grading, right? So this is probably most important thing now that students should have when they are checking or when they are sampling a class. So how are we going to grade it? It's very simple. because the nature of the algorithms, I don't think we can do an exam. So there's no exam here. There's going to be most of its contribution from problem sets, right? So in this case, we'll have 4 problem sets. Have in mind that this is a 3-credit course, right? So it means that the load from your side is not going to be superior to 80 hours, maybe, including classes and all this. So that means that problem sets are not going to be super heavy, right? So what we have tried to do is design good examples for each of the topics. So we'll have a problem set on discrete planning, sampling-based, value iteration, and decision-making, right? Each of them, I don't think should be, at least we try this like last edition, should be more than 10 hours from your side, right? This is still time, but it's not like other problem sets from other courses. I'm not gonna say examples, but let's say that other problem sets are more heavy. So why? Because I want to do 4 problem sets, right? I don't want you to do less, because that way you will not get this variety. And at the same time, it's 3 credits, right? So I cannot ask you to do problem sets as if this course was like 12 credits, right? When actually we just have 3. So I think it's reasonable. You will see the problem sets. We will release first one on Monday, when we do this first class on discrete planning. I will comment a little bit more on that. You also have the agenda on when is the expected delivery day for each of them. So it's kind of separation broadly of 1 week. And the other big chunk of your grade is going to be final group project, right? So there's a little bit more explanation that I'm going to do later. I'm going to show some examples, but well, this is nothing new, right? Group project where I will give you some examples. I will give you some papers. You can extend some topics that we have discussed in class. We'll give you some pricing, I guess, but it's going to be depending on you mostly, right? So what you want to do. Of course, if some projects are not could not be qualified as projects, we will tell you, so please don't do this or do this other thing, but there's going to be some discussion between teams and us. And well, this is going to be a usual thing, right? So there's going to be a presentation, there's going to be a report, and so on. Okay, so this is the course summary. Calendar, if you want, you have this in Canvas. Next Monday is discrete planning, but if you want to know a little bit more about what is coming ahead, you just need to come here in Canvas and check this out. We have a question. Is it graded course, pass, fail? No, this is graded course. So if you submit all problem sets, probably you are going to be doing very well. But it's also possible that you submit a problem set that not all points are correct, right? Or maybe you submit it late. I'm going to come later to grading. And then you will not get maximum grades, right? So I think it's not, if you are on date, you should be doing excellently, but it's going to be graded, right? So just for you to have this in mind. It's a very good remark, yes. Okay, you see, last day is going to be final project presentation. So this is where everyone comes or meets in Zoom, we'll see, and well, you will do short presentation. Okay, course material. I'm going to try to share everything we have. So that means that every lecture has some slides. We will upload this. Maybe on some lectures I will do annotations. I will upload also these files with, I don't know, maybe little problems that have been solved or little comments. It's going to be up to you also, because we will release slides in advance. So I recommend you also to take your own notes. So you will have your slides in front of you, and then you can do annotations and well, whatever you find convenient. This is our hope. We will also release videos from lectures to be uploaded on Canvas if from Zoom. But if we do offline, we'll do recording from material on classes. And then we'll push this to the YouTube channel, right? So in case that someone misses this from Canvas or from YouTube, you can check out, well, you can check out videos on these both sides, right? Two books, we have, well, these two, Planning Algorithms from Laval and Reinforcement Learning. This is going to be used later when we talk about last lectures in the class. So this is including MVPs, and there's a seminar on reinforcement learning, or let's call this deep reinforcement learning, because reinforcement learning is very broad, right? I'm not going to claim we'll be explaining fully this, right? So we'll do like one approach, right? And then we'll show, well, we'll do this on a seminar, basically for you to get hands-on on these problems. We will also upload selected papers for each lecture, so then you can take a look. This could be also ideas for you to apply for your final project or whatever you think. But it's basically going deeper into each of the topics because, as I said, there's many algorithms for each of the classes. Will be yes, for each on each class there's going to be a lot of algorithms that are related to this, and of course the Telegram channel. So I think I have shared links in Canvas, and yes, in Canvas mainly. And if some of you has not already joined channel, maybe you should, right? Okay. So as I said, it's gonna be Zoom offline, blocks of 45 minutes. Today, I'm just gonna do like full, well, we did this little break with some questions, but later we'll do like blocks of 45 minutes, little breaks, and then we'll get back. Usually it's gonna be 2 blocks. Students are encouraged to participate, right? So that means that I'll try to read the chat. You can unmute yourselves, you can participate, ask questions. This is really something we are looking for. I understand that it's hard sometimes because you are there, you're looking at a lecture, and then you're still processing things while we move to the next thing. Yes, but if there's something you don't see clear, it's totally fine to do a question, right? So please think this as a positive thing, not just for you, but everyone in the course. Another thing is maybe you can take a look at the slides before, and then if you don't see something clear, just wait for when it's explained, and then we can have well, little discussion in case that there are some parts that are unclear. Recommendation is participate as much as you can. This online, sometimes I think it's a little more difficult, but that's why I'm kind of saying, yes, this is a good thing. It's going to help you. It's going to make you get better grades for sure. And once again, just try to be engaged, right? So from our side, we'll always be happy to answer questions, even in class or later, right? But from you, you need to ask, because ask, yes, let me clarify this. Ask doesn't mean 5 minutes before the submission deadline, having 1,000 questions. This is not what I mean by asking, right? What I mean is while we are in class or maybe later, just to kind of questions that could be helping understanding things. It's not just for problem sets. So for that, yes, of course, you will have questions. But the other thing is you could be asking also your other students in Telegram chat. So maybe some has some ideas. Okay, anyway, yes, I hope everyone is happy with asking if there's like things. If not, well, I think then we might be missing a little bit. If we do this online, I'm going to be asking you. So yes, that's awesome motivation for us to come in the same place. In Zoom, I think it's more complicated, but we'll try. Okay, let's talk about problem sets, right? Because after all, this is main part of grades, and this is where you are going to be spending most of your time doing problem sets. So let me explain a little bit. Python, as I said, is going to be, I think this is level to entry level to start any programming. So we'll try to make things as clear as possible. There's no big frameworks or other things we'll be working on. So it should be all self-contained also with minimum libraries, maybe few, but bare minimum number. Please allocate your time for doing problem sets. If you start, even if you think that you can do this last day, probably it's not the safest strategy, right? Each of these problem sets is around 17%. Roughly, I think it's 10 hours. So what I saw last year is that students were ranging from 4 hours to 12 hours. I would say that median maybe was, I mean, we didn't do statistics, but just like this asking, and if some people were, it was below 10 hours, definitely, but please schedule time on this, right? Because if you miss, then there's gonna be problems. And the problem is this one, right? So there's gonna be a penalty for your grade if you submit late, right? So we are giving time, I think we are removing material, but because we want to create all the problem sets at the same time, we want everyone, and everyone would be on the same conditions, well, deadlines are gonna be strict, right? So we have this policy that I want to explain this well, because it's not really a very punishing policy, right? It's not like, oh, you didn't submit, you're gonna get 0. It's not exactly like this, right? So this is what we call the fine-tuning penalty, or fine every hour after the first 3 hours, right? So it means that if you submit at 12:01 a.m., that's 1 minute late, you will get 1% penalty. It's not too much. If you submit at 12:50 or 55, you will also get 1% penalty, right? So 1 hour is kind of okay, right? And the penalty, I'm going to explain now what it is. After the first day, it's going to be 20%, right? And there's going to be a minimum because, you still want to, I want all of you to submit problem sets. So you will not pass the course if you don't submit any of the problem sets. There's going to be a minimum that is going to be 50%, right? So this is the minimum you can get. So you can submit this whenever you want, but then the maximum you can get is 50%. And this is how the penalty is applied. It's not multiplicative. Okay, so it's not multiplicative. If you have perfect score and then you are 1 minute late, the formula is going to be the following. You have your grade, which is 100, perfect score. And then you have the max possible grade. And the max possible grade is -1%. So this is 99%. So your grade is going to be 99. Okay. Let's say that you have your perfect submission and you are 2 days left, 2 days late. Okay. So that means here that you have 100 and the maximal grade that you can get, or let's say 1 day, it's 80%. Okay. So then it's going to be the max of the two, 80%. Let's give another example. Let's say that you have done a not very strong problem set. Say that you got 60% of your grade, and you are submitting 1 day late. Okay, so we have here 60, and the maximum possible grade that you can get is 80. So this is the minimum of the two. Right? That means that you are going to get 60. In this case, there's no regret. You did a okay problem set with 60 and you are not being penalized. So there's no regret. When is the maximum regret? When you do a perfect problem set and you are like 5 days late or whatever. In this case, you're going to lose 0.5% of your grade, right? So this is something that some students were discussing last time. Why is this? Because I don't want to penalize things a lot, right? So there's going to be penalty. The penalty, for some of you have already guessed, is going to be on excellent or not excellent, right? So if you are 1 day late, this is not excellent maximum grade that you can get. If you are 2 days, it's C, I guess, or D, right? So careful with this, because it looks that it's not punishing, but actually it does. So what you want, I think, is to be on time and submitting whatever you have, right? If you are being late, then either you have a weak problem set, or well, let's say that then you are going to lose points, right? Okay. Yes, this depends on Canvas. So Canvas has its date and it's telling you when you are late. So there's no discussion here. We'll just follow this. Why no discussion? Don't tell me, oh, I have this problem. It's fine. It's okay. You can plan ahead, right? So in principle, we'll not be doing exceptions, because this policy, I think it's very mild, right? So there's other classes that are following more strict one. And that's why people ask for permission and whatever. So we'll do the other way. We have a mild policy, but there's not going to be any any discussion, right? Unless, I mean, it's very, very strong one. Okay, you want to discuss. You want to discuss with us. You want to discuss with other students. This is very important. Copying is forbidden, right? But what copying means is you take one code, you copy exactly the same variables, and you put this in your Python scripts or your Jupyter Note, whatever you use. This is not okay, right? So if we find cases of this is plagiarism, and of course, problem set is going to be disqualified. And well, let's say that this goes against the code. It's called the code, right? On how to do classes, how to behave in general, and all these things, right? Anyway, talking with someone else is not forbidden. So if you tell someone, oh, how did you solve this? Oh, I did this. This is not copying, right? So you are just talking about things. You can even show, oh, look, this is the results I'm getting, right? So unless you share code, things are okay. Of course, if you, well, showing code, I think this is kind of, but I think, yes, it's very good to have discussions, and I think you will learn a lot. It's not just for people that do not know how to do things, but it's also for people to explain how they have done things. I think this is a way for you to solidify knowledge, right? So I really encourage everyone to participate, either if it's explaining, maybe you explain things one day and the other you are asking, right? So this is totally okay. You can write acknowledgements if you want in your problem sets when you submit them. That's also okay, no problem. And this is the condition that I was saying. All problem sets must be submitted, right? So you need to submit something. If not, will fail. You will not pass the course. So it's not complicated. Remember that you need 50%, but still you need to submit all problem sets. So my advice is try to be on time. And if you are not on time, try not to miss like problem sets by more than a day, because that way you can get like very good marks. If not, then it's gonna be complicated, more complicated. Okay, but don't worry, problem sets are, I think, manageable. You can do this in finite time, and again, compare with other classes, these requirements are not so high. So well, that's what I think. Maybe some of you disagree. Okay, attendance is recommended, but it's not gonna be requirement, right? So we'll have videos and so on. So usually the correlation of people that come and people that have good grades is amazing. So if you come, most likely, yes, you will have good grades. People that miss, I don't see them like for some time. They usually are late in problem sets. It's all related, right? So try to assist, but we will not follow if you are supposed to assist, by the way. So, but we will simply not consider this into the final grade. I think it's indirectly we'll see, right? So I think people that do well usually assist. Okay, if you think that something was created incorrectly, you can ask for grading policy. So just send an email to all of us. And well, yes, academic integrity, there's a link in Canvas. So, I mean, it's common things, right? So the main, most important one is copying is forbidden. Right? Okay, let's talk a little bit about final group project. So it's gonna be a topic related to the course. Don't worry, so we'll be doing lectures now. You will see a little bit of everything. I think you can do an informed decision after some lectures, not now, right? So now maybe it's about looking for a group, looking for students. Maybe if you have some of them, we will announce when we need definite list of students. But in principle, we want a list of 3 to 5 students. Ideally, it's four students. Oh, this date is incorrect. No, wait, this is correct. Yes. Proposal. Yes. You have assignment in Canvas, December 8th. Yes. So proposal means that there's going to be a one page where you put title, you explain a little bit what you want to do, you write how you're going to do it. So this is also important. And then you'll have like 2 weeks almost of working on this project. It will finish with a presentation and a report that you will submit. Okay. Let's give an example of past projects because maybe this will help you a little bit, right? So in this case, team A, I think it was working on rapidly exploring random belief trees for motion planning under uncertainty, right? So what it means is that you have growing uncertainty as you are moving. You want to get to this position, and you have areas where you are more certain about your state. In this case, you are more certain about this light area. So imagine this is light versus dark. So basically, if you move here, you will have like more certain, less uncertainty, right? So this is a topic that, well, it was described in one of the lectures. We'll do a little bit, but it's going to be later, I think lecture 7 or 8. Second project was bringing learning to classic motion planning. So in this case, you don't see, but, or maybe you see, right? So these are different learned samples that they were using. And the idea was to combine, this is a sampling-based planning mechanism that was using for sampling learned distribution, right? So in this case, there were different strategies, and then they were showing like trade-offs, right? Like for instance, here, this one had more exploration. This one was a little more focused, and well, the plan actually I think was just getting passed through these things, right? So it's kind of passing through these small gateways. Okay, interesting topic. Actually, I would say that this is very research relevant. Bringing together learning approaches with planning, right? So you can have like totally end-to-end things, but sometimes these hybrid approaches have advantages. Other projects, Evader Pursuer zero-sum game with Monte Carlo tree search. So this is the environment. This is similar to one of the problem sets, by the way. And the other was comparison of different algorithms for Pacman environment. So Pacman environment could be thought as a game also. We will discuss about games in lecture 7. And well, let's say that there's different ones that they can do. In this case, this is a particular method of reinforcement learning that they were using, but they also tried other methods there. Okay, I think that's it. That's all material that I have. If now anyone has any comment or question. Oh, I see some questions here on the chat. One, allowed late submission? No. No. Policy is the one that I described. Is it possible to make own project or do it alone? You mean without group? I would say try to find a group, right? So if not, we will assemble people that are without group. And the reason we want you to collaborate is because it's kind of a different process. So if you want to work alone, you have problem sets, but with collaboration with others, you put in common other skills that are necessary. So this is also an important thing. So I would say that individual final projects, in principle, no. We'll find groups, don't worry. We can discuss details also. But my opinion is that the advantage is not, I mean, the advantage is that you will get expertise into some method, and at the same time, you will collaborate with others, which is important skill also. Task distribution and all these things. Okay. So I think that's it. If there's no more questions, I'm gonna stop sharing. Oh, well, first of all, I'm gonna stop recording.